Greetings everybody. So here's a problem from our assignment on MyMathLab, and I think it's a good problem to do, and here's the reason. I think the way that this question is described and presented to us here makes it seem a lot more complicated than it is. So I'll show you my own way to understand this, which for some people might be easier than trying to think about it the way that it's given. So let's go about it like this. We're given a series. Sum from k is 0 to infinity of negative 0.3 to the power k. Terms of that series would be 1 for the first term, because you start with k is 0, then negative 0.3, then positive 0.09, then negative 0.027, and it goes on from there. Now, what we can tell about this series is that it's geometric. R, the common ratio, is negative 0.3, and the first term is 1. All right? Such a series would converge to 10 over 13. All right? And I'm using the formula for the sum of a geometric series to get that. Now, this is not the first video that I'm making and showing you about geometric series, so I'm not going to explain, in this video at least, how I know all this, but working up to this point, you should be able to tell what a geometric series is when you see one, okay? Now, here's what this number means. I think to understand this question, I need to understand what does it mean to say this series converges to 10 over 13, okay? So we could look at it like this. I could say the more of these terms I add together, the closer that grand total is going to be to 10 over 13, okay? We could visualize that if you wanted to like this. So here's a little graph of the partial sums. If I add the first term of that series together, which is just the first term of 1, I'll get 1. If I add the first two terms, I'll get 0.7. If I add the first three terms of that series, I'll get 0.790. If I add the first four terms of that series, I'll get 0.763. Now, what you can see here is the more terms I'm adding, the closer those grand totals are getting to this red line, which on my graph represents what the series converges to, which is 10 over 3. Sorry, what was that? 10 over 13. Was it 10 over 13? Yes, okay. So 10 over 13, which turns out to be about 0.7692 with a little rounding. So there, 10 over 13. Now, so yes, every time I add another term, the more terms of that series I add, just visually, the closer these points, which represent those partial sums, get to that red line. And so I guess you could say just numerically, the closer these numbers get to that number, all right? Okay, so that's the first thing I think that you'll have to understand to really understand what this question is asking for. Now, so that gives you a way to think about what this means. When this series is said to converge to 10 over 13, that's what we mean. Now, here's the way I would explain the problem in that context. So here's another graph kind of like the one over there. And I'm just saying like s sub n minus 2, that's the sum of the first n minus 2 terms. S n minus 1 is the sum of the first n minus 1 terms. Sn is the sum of the first n terms. And you see the same kind of pattern where the more terms I add, the closer the grand total gets to whatever the series converges to, 13 over 10 in this case. So the question is really asking about how close these partial sums are. How close are these points, which represent the sums of the series, to whatever the series converges to? Yeah, it gets closer the more terms you add, but let's talk about measuring how close. So I'll say you see these gaps here between the sums and what the series converges to. We'll call that capital Rn, the remainder. It's just the difference if you subtract between this number and that number, okay? But we'll call it the remainder. Here's what this question is asking. It says, how many terms do you have to add of that series so that the remainder, which is how close that sum is to what the series converges to, is less than this? In other words, how many terms of the series do we have to add to get this close to what the series converges to get 10 to the minus 6 power close to this line? That's all it's asking. Okay? So that gives you another way to think about that question. Sure, the more terms you add, the closer the grand total gets to 13 over 10. But how many terms do you have to add to get this close to 13 over 10? All right. Now here's how we'll solve that. The remainder, meaning this difference right here, this gap, is found by the formula r, the common ratio of the geometric series, to the n power over 1 minus r, absolute value. It's absolute value because depending on how you subtract to find this gap or difference, you could get a positive or a negative number. Okay? All right. Now, I want to see what does it take to get our remainder to be 10 to the minus 6 power or smaller. So I'll just set it equal to 10 to the minus 6 power. And I assume because these points get closer to that line as you go forward, that going beyond that will get me less. Okay? So I can set it equals and just say, well, if I go any past that point, then I'll get the less than. All right. So here's my remainder formula. Common ratio of the series is negative 0.3 in power 1 minus negative 0.3 net to equal to 10 to the minus 6. Okay. So I gotta solve that equation somehow. Now, let's do a little simplifying. Now, what's that number down there? 1 minus negative 0.3, that's 1.3. Now look what I did between these two steps. I dropped the negative and the absolute value. So the only reason the absolute value is in this formula, as I mentioned, is because depending on how you subtract to find this gap or this difference or distance, how close this is to that, depending on how you subtract, you could get a positive or negative. But I mean, I just want to know the number, all right? I just want to know what is this. So if the absolute value only corrects for the sign, and if that negative right there with that negative 0.3 is the only way that this in here could be negative, if I just drop that, I can not deal with the absolute value and get something much simpler. Okay? All right, so that's why it's acceptable to take from this to this. Okay, now I'm going to solve this. The way I'll solve that, given that I want to solve for n, because if I solve for n, that will tell me how many terms am I going to need to get acceptably close to what the series converges to. To solve for n, I'll multiply both sides by 1.3. And then because the n is an exponent, this is the kind of equation you solve with logarithms. Okay? So logarithms is something you learn about in algebra. I wouldn't mind reviewing that at all, but I'll say the way that would work is that if 0.3 to the n power is this number, then n is log base 0.3 of that. Okay? Which this you may evaluate in your calculator directly. I have with me today, I have a very basic scientific calculator, and I can do standard logarithms. I can't do log base 0.3, but maybe you can. Okay, so maybe you'll calculate this directly. If not, if I have to use my basic calculator, I'll use the change of base formula. Okay, this is called the change of base formula. Either way, you'll get n is about 11.257 and so on. Okay, so we've solved it. Now, keep in mind what we're solving for. I'm trying to tell you how many terms of that series do I have to add to get desirably close to what the series converges to. I can't add 11.25 terms of a series. The series has 11 terms, or 12 terms, or 13 terms, on to infinity. It doesn't ever have 11.257 terms. So I have to round. But should I round 11.257 to 11 or 12? Well, we'll always round it up. The reason is I set it up to figure out how to make this gap equal exactly to 10 to the minus 6 power. The question was, how do you get it 10 to the 6 power, 10 to the minus 6 power or less? It turns out because the answer is not a nice whole number, you can't get exactly at that. But if you go to the next term, you can get below it because these gaps get smaller as you keep going. All right, so we'll always round that number up. We might solve this, we'll get some kind of decimal, even though you would ordinarily round 11.2 to 11, not in this case. We round it to 12, okay? All right, now I want to do something even more tangible than what I've showed you. So far, you see how to solve the problem. But there's even a more basic way to see it. I hope you understand how what I'm about to show you is even simpler and more direct than what I've gone through already. But here's what it says. What we're saying is if you add 12 terms of this series together, then you will be this close, 10 to the minus 6 power, to what the series converges to. So look what I did here. Here is the first 12 terms of the series. Okay, I added them together and I got that number. That's what the sum of the first 12 terms of that series is. Now, if we're right, then if I subtract what the series converges to minus the sum of the first 12 terms, it will have to be less than 10 to the minus 6 power. And if you calculate that and you subtract those numbers, it is. Okay, so there it's demonstrated. Yes, if you take this series and you add the first 12 terms together, you will get closer than this to what the series converges to. So there it's proved, like you see the number right there. But we'd also have to show that if you added only the first 11 terms, this wouldn't happen. If you added only the first 11 terms of the series and redid this number, their difference, would not be smaller than 10 to the minus 6 power. Okay, so that's a demonstration that we can do on top of everything to see that the number is right. Okay, now I'll let you take away from this what you want. Okay, if you like the demonstration in addition to just the solution, you could do that. But either way, I really hope, just to help your imagination and to get your thinking in the right direction with questions like this, that you see the partial sums like this, that you can visualize it, you can see like right there in the picture, even if you don't have an instinct with the numbers, that the more terms you add together, the closer you're getting to something, and that's what the series converges to.